All right, good afternoon, everyone. Welcome to the May 30th, 2018 edition of the VLab Forum. This is Steve Smith, Director of NOAA's VLab. I'm joined in the VLab Forum studios here in beautiful downtown Silver Spring in the shadow of the giant acorn by John Chattel, Technical Production Manager, VLab Forum. And very pleased that we have a really big crowd, not surprised at all. We have the VLab Forum is, to remind everyone, is to get a look at research and development projects that are working their way into Weather Service operations or NOAA operations, or may inform Weather Service and NOAA operations at some point so that we can be looking ahead. We've been attempting in the recent months to book some speakers who are looking on the cutting edge of things related to IDSS, Decision Support Services, a big thing for the Weather Service. And today, I'm very happy that our speaker is Dr. Brenda Philips from University of Massachusetts Amherst. Dr. Philips presented a version of this talk, probably a 10-minute version or less at AMS. That's where I saw something like this very, very interesting and relevant presentation with regard to IDSS, so we decided to invite her, and she cordially accepted the invitation, so we're really lucky. The format of the VLab Forum, to remind everyone, is about 30 minutes or so of content, followed by about 30 minutes of Q&A. Ask that you hold your questions unless it's really critical until the Q&A part of the hour. But when we do get to that, really encourage folks to use the raise your hand feature of the GoToWebinar. John Chattel will unmute you so that you can ask your question directly to Dr. Philips. You can also use the chat feature to type in a question, in which case John will relay the question on your behalf to Dr. Philips in that way. Also a reminder that the VLab Forum presentations are recorded, and we will be uploading the recording to the VLab Forum website shortly after the conclusion of this session. So without further ado, Dr. Philips is here to talk to us about context-aware weather warning systems. Dr. Philips?
Great. Thank you very much, Steve. Thanks for inviting me, and thanks to everybody here who has linked into this webinar. I'm Brenda Philips, and I'm a co-director of CASA. And CASA stands for the Center for Collaborative Adaptive Sensing of the Atmosphere. And it's a research center. It's headquartered at UMass. It has partners: Colorado State University, OU, University of Puerto Rico, Mayagüez, University of Delaware. And it was originally founded in 2003, and it was focused on creating a new paradigm for warning system and response through the deployment of X-band radars and other kinds of sensors. So in addition to directing the research center, my role in CASA has been to lead our socio-technical research, socio-technical systems research. And I think, as you all well know, severe weather warning systems are a great example of a socio-technical system where human interaction with the science and the technology really drives the effectiveness of the whole system. Before I get going in the presentation, I'd just like to acknowledge my collaborators and funding sources. CASA has been a big project over the years, and you can see that there are many different disciplines involved in the academic sector, from radar engineering to social sciences to computer sciences to geography. We're very involved with practitioners, especially now in the Dallas-Fort Worth area, and those are people in emergency management, and we're very involved with the local Weather Service office. And our funding primarily comes through the National Science Foundation for this particular project, through the Atmospheric Sciences Directorate, through the Computer Science Directorate, and through their Partnerships for Innovation program. So I'd like to just start by talking about severe weather warning systems and give the context in which I'm going to talk about severe weather warning systems. Severe warning weather systems, they link weather hazards, warnings, and people in time and in space, and they have the goal of basically motivating people to take protective action and take the appropriate protective action. And Maletti and Sorensen, who are, you can see they're cited right here, did some great work that really frames what warning systems are. And they really talk about a three-part system. They talk about a detection subsystem, a detection/forecast subsystem, where a forecast or an observation is identifying hazards based on both technology and human expertise. The management subsystem uses that scientific information and then translate it into warnings or alerts that go out to different segments of the public. And in the response subsystem, people actually interpret and receive these warnings and decide whether they're going to take protective action. And there are these three components of the warning system, but there's also a lot of intervening forces. There's the natural system, there's the built system, and there's a social system that all impacts that. And there are official warnings and alerts like the NWS warnings, of course, and there are all sorts of informal warnings like telephone calls and social media and even visual cues that people use to respond. So, it's a complex and very interdependent system. And if you have improvements in the other, they actually can result in improvements in the, in the end response of people if you understand how to translate those improvements from one end to the other. I'd say right now when you look at the warning system, it's primarily a broadcast system, and where the official warnings go out, the informal warnings go out, and it's up to the general public really to place themselves in the warning, decide how much they are at risk, and decide whether they can and will take protective action or protect their loved ones. And the other thing to think about is that the warnings are mostly disseminated to broad groups, either people within a warning area or people who might be within a certain region or something like that. But I actually think that warning systems are about to go through a real shift, and that's due to several different advances in technology and our attitudes toward technology. And one, I think, primary driver is the phone penetration and usage. This picture on the bottom shows a group of students. I think it was called the cell phone apocalypse or something like that, because they're all just walking like zombies, staring at their phones. And there's no doubt that we've become very attached to our phones. The Pew Center survey showed that 97% of the population uses mobile phones and 77% of the population uses smartphones. So it's resulted in this explosion of social media usage. It's impacted our attitudes towards sharing and privacy. Just anecdotally right now, I have on my Fitbit, and it seems that I'm willing to send my heart rate and how many hours of REM sleep I just got last night to a server somewhere. And I'm doing it because I'm figuring I'm going to get some sort of benefit about it. So this whole concept of what you share in privacy has really changed. The other factor is the development of the Internet of Things, and the Internet of Things, or IoT, enables devices, embedded sensors, mobile phones, actuators to be connected over the Internet. And it allows us to measure new things and create and explore new relationships among those measurements. And I think it's important to note that the Internet of Things has allowed us to actually sense people, their locations, their behaviors, and their attitudes in real time through mobile phones, but also through other devices. So I think that's really interesting that we're starting to be able to put together some environmental things, some infrastructure sensing, and people sensing, and thinking about, how do we position that, and what are the opportunities for severe weather warning? I think that's a question that I'm very interested in, and that our group is very interested in. And so, you know, when we talk about the opportunities for severe weather warning systems, you know, the one question is, how should we integrate the current broadcast paradigm that we have with the potential for dynamic and personalized warnings? Can the Internet of Things help us better understand the linkage among the different warning system components? If you think about human interpretation and response to weather information, new types of weather information, we're very interested in high-resolution radar data because our project is based on that. But there's also ensemble forecasts and many other kinds of weather products and information and capabilities that are coming at, as well as what are the new warning policies. And then lastly, so what are the innovative ways to research these types of questions given, you know, the complexity of the warning systems that we described earlier? And so this is really going to be the topic of my talk today. First, I'm going to give a background on CASA and what we have now, which we call the CASA Dallas-Fort Worth Living Lab. And so it's a living lab of radars and people, and I'll describe that later on. I'll talk about the context-aware warning system that we have operating in the Dallas-Fort Worth Metroplex, and then give an example of current research projects. I picked 3 related projects. We have many going on, but I wanted to give a flavor of what we're doing and what we're finding out and the challenges in those projects, and then also talk about broader implications and next steps. So in terms of background, just a little bit more on my background. Again, I'm co-director of CASA, and CASA was this National Science Foundation Engineering Research Center. It went on for 10 years with a large $40 million grant and involved Colorado State University, OU, UPRM, University of Virginia, UDEL, and University of Colorado, Colorado Springs. And one of the interesting things was that our research was conducted through a lot of test beds and through a lot of real world contexts. And so we operated a test bed in Oklahoma. We also operated one in Puerto Rico, where we were able to implement the technology we developed and then continue to iterate on the development of technology by showing users data and getting user input, as well as doing technological validation. In terms of the research that I've focused on, I'm really interested in this notion of making links between the natural, technical, and behavioral parts of warning systems. I'm very interested in how you conduct research within the context of these living lab test beds, because it tends to be very messy, and I'll talk about that a little bit later on. And I've had the role of, I hear this term in multidisciplinary research papers, of a spanner, someone who can kind of bridge different disciplinary researchers so that you can really create a kind of an overarching research project where everybody finds interesting questions to ask, and where the, you know, the whole is, of course, greater than the sum of the parts. Some of the images you see, this is me quite a long time ago, actually, maybe, I don't know how long ago. But anyway, this is in the hazardous weather test bed. CASA was in the hazardous weather test bed for probably 5 or 6 years, where we not only brought in NWS forecasters from all over the country to look at the data in the Oklahoma test bed, but we also engaged with emergency managers who are actually within our Oklahoma test bed so that we could show them real-time data and understand how they respond. This image on the bottom is the radar footprint of our Dallas-Fort Worth test bed. So I'm going to go on and talk about our Dallas-Fort Worth Living Lab. It's been going since about 2011. And it's really, again, the whole end-to-end warning system. It's the sensors, the weather information, The weather information goes out on various distribution and dissemination technology to our stakeholders and the public. And it's demonstrating the benefits of high-resolution atmospheric sensing, looking at urban scales of weather, looking at radar observation gaps, and it enables multidisciplinary research in a live environment, the physical, the technical, and the social sciences. And it has this flexible infrastructure for technology development and RTO. I'm not going to talk about this in this talk, but one example is that we have commercial radar providers who have been able to place a single radar within our network and integrate into the system and demonstrate and, test the value of X-band, and which has led to subsequent sales for them. So that's an example of a more technology-based R2O. And then also, we have worked with the community, so we view this as a co-creation opportunity. We're not studying them, we're basically creating this together. And so it's this ongoing process of iteration and design and improvements that we're doing based on this very close relationship we have with the community. The concept of operations for the Living Lab is that we have a 7-node radar network, and they're dual Doppler, dual polarization radars plus other sensors. They operate year-round when there's precipitation in the network, and they generate real-time single and composite radar data and derived products, including quantitative precipitation information, rainfall rates, hail, wind, nowcasts, and forecasts. The CASA data is available to the Fort Worth forecast office on AWIPT2 as well as to Southern Region headquarters. And CASA products are also available to the broader emergency management community on a CASA WX website for real-time operational use of very low latency. Right now, we have about 1,500 users, about 750 plus local public safety users from North Texas cities, and about 600 app holders with our app. You can see in this image, this is again the radar footprint. The radars are overlapping. The range is about from 40 to 60 kilometers. And this is a composite reflectivity product that you're looking at right now over the Metroplex. You can see it covers really the heart of the Metroplex, which has a population of about 7 million people. So we work very closely with the North Texas Central Council of Governments. And through that, we've created these collaborations where the community contributes sources for the installation and operation of the network. We work based on a memorandum of agreement. And the North Central Texas Council of Governments has created a membership fee for local towns and communities that support our radar operations. So they see the radar information in real time. And in the last 5 years or so, we've collected close to $1 million in fees from the community. And so that allows the radar network to operate, and then we do research on top of that as well as support the real-time operations and learn from that. And you can see the different communities. This community is in Midlothian, and they found corporate sponsorship to build a tower. Other communities like Addison went to their city council and got money for the installation and operation. They didn't have to pay for the radars because the radars actually came from the original CASA grant. And so I just wanted to give you examples of how it's been used in real time. And again, the data goes into the Fort Worth forecast office, and and they have it in AWeBs, and they have used it to issue warnings when the data is valuable. They use it along with all their other data sources, of course, NextRed and TDWR. But this is just an example of it used in a warning decision, a tornado warning decision. And the interesting thing for us is that, this is very high resolution, low-level information, low-altitude information. And so when they talk about the data, they are always able to talk about it either on a street level or on a neighborhood level basis. So for instance, you can see for this warning language, and this is the warning that was issued, that there was a tornado, a severe thunderstorm capable of producing a tornado, on Highway 67 between Alvarado and Venus. So it's very specific in terms of where it is. And we've seen that a lot in terms of the way that the data is used. And that's really very valuable in a high population area where you really want to warn the smallest portion of the population, and you want to make them aware very geographically, specifically where the risk is. Another example is a pilot that we just started this storm season, where we're allowing media stations to air our data during events. And this is just an image of, this is Dave Finfrock. He's a beloved weather person down in the area, displaying the data and talking about it for a recent event earlier this May. So now I'd like to get into the context-aware warning systems. And what we did as part of the warning system that we have operating in the Dallas-Fort Worth Living Lab is that we created an app, and we call it CASA Alerts. And it can deliver targeted alerts to people based on their location or based on locations that they specify. And people can define their alerting preferences. And right now we're doing the alerting by distances. So you can see for a tornado reported, you can have it if it's 20 miles or closer on top of you, or a funnel cloud reported 20 miles or closer, or kind of on top of me. And here you can see how people can specify the locations. You get the information both as text and visual information, and then we can deliver surveys, and or we can get reports from people on either what they experienced, or we can ask them about the warnings. And we can do this in near real time, so that people are really responding to the event right away in how they experience it. And that's really a great way to get impressions, because frequently if you ask people too far after, there's a recall bias where people tell you what they should have done versus where they actually done. So the closer you can get to the time that it happens, usually the better the information that people can tell you. We've recruited app users. We have over 600 app users now, and we're trying to expand that number greatly. And because of the relationships in the community that we have, we're about to go out with a big push to get people to download the app. We've collected a random sample, a small random sample of people. So we do have an official random sample, but a portion of the sample is also a convenient sample, and we'll be using a convenient sample going forward. This convenient sample is recruited, one, through the communities, which I mentioned before, and two, we've been doing recruiting on Facebook and on Twitter to get users. We're doing geographically targeted recruiting for participants there. Participants, they sign an IRB, or they give their approval to be part of a human subjects experiment, and that includes allowing us to track their location, and that's how we're able to give them targeted alerts, as well as analyze data after an event happens. Each user can fill out a pre-experiment survey, and on that survey We get information about their perceptions, demographic information, a lot of it, whether they've had experience with different kinds of hazards before, a little bit about their perceptions on false alarms and missed events, and whether they prefer one to another for different hazards. And that we can use as a basis as we try to figure out, what kinds of segments there might be, if there are any. And then we can also send them event-based mobile surveys, mobile phone surveys, where we can ask them when a particular event happened, did they receive a warning? Did they find it useful? Did they take any kinds of protective action? And we can do that over time so that we can get a look at both, severe events, run-of-the-mill events, and we can see over time how people respond. And lastly, all of this information goes into a database so that we're able to link their location, their survey responses, even the weather data in an archived database so that we can start to make linkages and understand what's going on. And you'll see examples of these when I talk about the research project. So the context-aware warning system basically links, it links hazards infrastructure, policy, people context dynamically and time and in space. And so what I'd like to do is just go through this piece by piece because there's a lot on this slide. So if you think about the different kinds of risk people experience as they're impacted by hazards, there's an environmental risk, and we have a way of measuring those with radars, and we use models to be able to do that. This is an example of a rainfall rate from our quantitative precipitation estimation product. And that is very overlaid with infrastructure risk. And what you see here as an example of infrastructure risk, and this is actually all over the city of Fort Worth. So this is all happening over the city of Fort Worth. So what you see here is we mapped watersheds, and you can see the shape of different watersheds within the city of Fort Worth. And in talking with the stormwater managers, we understand what the different thresholds for risk for the different watersheds. Right now, in talking with the stormwater managers, we're using a rule of thumb where they say where the accumulation exceeds a half an inch, then there's more flood risk. And so we're basically overlaying infrastructure risk and the environment shown by the radar data to figure that out. And then once we hit a threshold, then there can be a management policy decision for alerting. And so this is this square down on the lower left. And what you see here are the same basins that are up here, the same watersheds, but they're colored by green, yellow, and red, showing the level of flood risk they present. And so the red, is over the flood risk threshold, and so you could send out alerts based on that. And you could send out alerts based on a policy rule that might be that you alert people within 5-mile radius of this area, or you could alert people on roads. It's actually very flexible how you do the system. And then the last thing you have in this system are the people, and so we know where the people are through their cell phones, and they're going about their daily lives, and they have preferences for being alerted, and we have their demographics, and then so we can alert people who fall within these risk areas that we define. And all of this data, and so this data can go out in terms of alerts. Right now we're doing automated alerts. We're not doing manual, but we will do manual. And then we can also send them a survey and say, what did you think of those alerts? Did you like it? Did you respond? Did you not? And then all of this spatial and temporal data goes into a database and along with the survey results, where we can do analysis later and learn about how people respond, and then feed that back into new rules. And so I gave an example just now that was a flooding-oriented example, but you could have a tornado-oriented example where the environmental risk, again, is measured through radar. And this was a small tornado that actually occurred in the Dallas-Fort Worth area. You can see right here. But the infrastructure risk in this case might be people on roads, and so you'd want to track the road network. And the management policy might be the emergency manager's activation of sirens and how they're going to do that based on the risk. And again, they can direct it to the people who are going to be impacted by the risk very precisely. And again, we have this ability to analyze the information. And so what I'd like to talk about now is a couple of different research projects that we're working on. So the first is linking the public's perception of rain intensity and radar data. And it's a pilot study that we did. And if you think about it, when somebody says, it's raining really hard, we right now don't really have a good idea of what hard means. Does it mean, the equivalent of 3 inches an hour, the equivalent of 5 inches an hour? And we don't necessarily know at what point people really start to take, start changing their behavior. And so this is the type of thing that this system can do. And so we did a pilot study, and a survey was sent automatically to all app users when more than 8 people were in a heavy rain area. And we defined heavy rain as more than 3/4 of an inch of rain in the 15-minute time period. And this was done to a convenience sample, and we had 437 responses to rain events as they occurred over about a 1-year period. Now, this is the first time we did it, and so there were some issues with the survey tool, but we did get some good results, and I'm going to show you one specific case. So you can see here in the app, what we did was we sent people a survey, and we said, in your opinion, what was the hardest it rained in the past hour, and they could choose what that was. And then we said, based on the warnings, did you change your plans at all? And if you did, what did you do? And then talk about the frequency of the updates and warnings on the rain. And so I'm going to show you results on one specific day that can give you a sense of how this works. So this is a May 23rd, 2017 event here. And so let me just explain what you're seeing here. I'm hoping everybody's seeing the animation of the rain data going through.
We are, Brenda. We can see it.
Okay, great, very good. So the dots represent people and their location when they completed a survey. And the color of the dots represent their perception of the rain, whether they thought it rained very hard, which is the dark red, to not at all, which is the blue. What we also superimposed is the radar data that goes about a half an hour before and after the people answered the questionnaire, the survey, so that we can see what kind of weather they experienced. And again, the warmer colors, this is a 15-minute accumulation product. So the most intense, it was at 1 inch every 15 minutes, which is like the equivalent of 4 inches an hour of rainfall, which is a lot of rain, even for people in Texas. And so what you can see, which is actually very good, because this is our first time doing this, and to try to really understand, could this be a way that we could actually start to learn about how people feel about rain data, is that, the people in the red spots were experiencing the most intense level of rain. And we actually have the amounts that they were experiencing so that we could take an average of those over time, and so that we can define what a user perception of heavy rain is based on a radar based on radar data over time as we gather more and more of this. Another interesting point here is this person who's in the moderate area, and you can see that this cell kind of, the intense part of the rain kind of splits. And so this person actually received a more moderate rain during this. And then the people who said it didn't rain at all didn't experience rain. So we're really pleased with these results, and we've tweaked the survey, and we're going through this current storm season collecting more data. Although I will say it has been the quietest storm season in the Dallas-Fort Worth area that we've experienced since we've been there. So I'm worried that we're going to get enough data, but it will rain again, I'm sure. So this is a really interesting result, and you know, so we did this with rain. We also asked people where they'd like to go, whether they'd change their behavior, and it was only at the very most intense rain that people said that they changed their behavior, and that seems pretty typical of people who are from this area who experience a lot of severe weather. They're pretty tough, and it takes a lot. But if you actually want them to change their behavior in the moderate rain, then you're actually going to have to do a lot of persuasion to do that, because it's not what they naturally do. So that's how this information, you know, can potentially be used. So the next experiment that we have is in human mobility research and individual what we're calling footprints. And if you think about the places that you go and when you go there, there are probably 3 or 4 places that you usually go, maybe even just 3. It's home and it's work, and maybe it's your children's school, or maybe it's a gym. And people are, by and large, I think, pretty boring. And so there have been studies. There's been a good study by this guy Song in Nature that shows that they're very predictable, that human mobility patterns are very predictable in time and in space. And so we looked at 240 app holders' location data, sampled every 5 minutes over 6 months, and created their own mobility patterns. And again, we're calling them footprints, individual footprints. This is a convenient sample. And then we used a kernel density function to determine their time-weighted location density and their activity-weighted location density. And you can see this. This is a time-weighted density on the side here. And again, you can see these patterns of people going back and forth to work and to one kind of secondary place kind of over time. This is just showing you a person over 2 weeks, and and these hot spots represent work and home for them. And this is another view of a footprint along with the commuting pattern. So this is a footprint at all times, and again, this is home and work. And then you can see, through the location data that we're getting this person's commuting pattern. So it's really interesting and kind of creepy at the same time. And this is the footprint during commute time, where you can see that there's there's more density in the path that they commute. And this is important information, I think, for weather warning. So we did a basic descriptive analysis of these 240 footprints, and the results of those footprints are here. And so what you're seeing here is that this is the percentage of the density. So this is 100% of their density. So that's their whole footprint and the percentage of the area. So 100% of their footprint is 100% of the area, the median number of nodes that they had, and then the median square miles of a footprint. And so you can see these going across. But the interesting thing here is that, there's an 80-20 rule operating here. So we saw that people spend, 80% of their time in just 23% of their footprint. You can see how this goes down from the 100% all the way down, to the 10%, but it goes down initially very rapidly. And so when you think about warning for people, that's actually it gives you a really specific area that you can concentrate on for warning people. I mean, that's where they are most of the time, and that's what they care about. That's where their home and their work and their daily activities exist. And so, I think footprints are important because Personalization, there's a lot of literature that shows that personalization is crucial in the warning perception and response process. People have to think that the warning is going to impact them and their loved one before they'll actually take it seriously and figure out a response. And they also contain the important locations that actually help with personalization. Home, work, school, and commuting, these are all important areas. And then lastly, and I'll talk about this a little bit more later on, footprints can become like a spatio-temporal artifact that can actually represent people in operational warning system technology. If you think about right now, we think about people as just as an individual in one spot. We don't think about all the potential spots and when they're there and what they're likely to be doing. If we can think about that, that might be a really interesting way to warn people. So I want to talk about a flash flood study here that we did last year. And what you see on the left side is this is the CASA QPE data, or rainfall data. And this purplish area and the green area is an area that's defined as heavy rainfall and higher risk for flooding based on the city of Fort Worth. This is the city of Fort Worth infrastructure. And so on this side, you see the NWS flash flood advisory that was issued for this, that brackets this area of risk. But you also see how our system can kind of contour warnings along the risk area. And you can see that this matches the risk area here on the radar data. And then we can also send out alerts based to people based on this area, whether it's in a certain buffer zone in this area or just in this area. And interestingly enough, this is where there were 3 high water rescues for this event and about 13 or 14 stalled cars. And they all happened within here. And this is in the center city, which has kind of a poorer flooding infrastructure. So that's why they typically see the events here. But you can see that we're able to narrow down the area of risk, and not only do that, but be able to alert people, through phones that this risk exists. Now, this is a case study, so we actually didn't go and alert people. This is more to look at the feasibility and to understand what this might, whether this might work. We'd want to look at more cases before we actually started alerting people. The other thing I'll also say is that I don't think that this is not, this is complementary to National Weather Service warnings as they exist, and provides an additional layer of information, of more geographically specific information as the event evolves. We don't necessarily see this replacing warnings. It's really what can you add and how can you make people even more aware of what's going on. And so if you think about this warning, and you think about 3 different people who have the app, and you think about their footprints, you could think about different ways of warning people. So this is here's a person, and here's their 80% footprint. So these are their hot spots here. And another piece of information is that this event happened on a Sunday night. So if this is this person's home, which it probably is, and this is this person's work, this person is probably less concerned about the flooding event, but probably wants to know about it, and you could address them in that way. This person, lives and works and is all in this high-risk area, and so they would need to be, warned in a different way, whereas this person may not even be involved in it. And so it gives a way to think about really personalizing warnings and thinking about, people's individual context. So in terms of broader implications, I showed this image before, and what I wanted to emphasize here is that instead of representing people as individuals, we can represent them as their kind of temporal and spatial footprint. And we even probably know the probability that people are likely to be in certain places in certain times. So just as we have radar data, which shows risk at a certain level, and we understand, the probability of something being correct and things like that. We can start to actually do that with people, and that's an actual artifact that you can incorporate into a warning system. And so I think that's actually one of the really exciting, future results of this kind of research that we're doing. And we're just at the very, very beginning of this, but I think it's potentially very, very promising. And so, if we think about next steps, we've identified some of these, interesting ways to link perception and radar data. And the question is can we create better warning communications out of that? And do footprints make a difference? And one of the experiments that we'd like to do is communicate to people based on these footprints and their anticipated locations and see, do they perceive them better? Do they respond to them better? And we can understand that through this infrastructure that we've set up. Another area of really interesting research would be to start to use data analytics to look at not only to look at the people's response and the weather and the infrastructure, and to figure out warning strategies around that. And then, of course, there are policy issues to figure out how would you link individualized warnings and warning policy, and then also a larger issue of dealing with this living lab is, addressing issues of convenient sampling versus a truly random sample, and generalizability and the confounding variables that you see in field experimentation. So that is a brief overview of what we're doing. And if you have questions and comments that you can address in this seminar, I'd be happy to address them either through email, or you can also give me a call. So thank you very much.
Thank you, Brenda, for a very stimulating set of ideas and content to chew on. So at this point, we'll open up the GoToWebinar for questions. So if you'd like to ask a question directly, please, to Dr. Phillips, please use the raise your hand feature, or type in a question in the chat, and John Chattel will unmute you. Brenda, I'd like to start out with one for you. So at least in terms of weather service, sort of implicit in our, our practices with warnings is, they call it like the marination effect, where we have this sort of very tiered structure where we produce forecasts, and in the case of severe weather, the Storm Prediction Center does a convective outlook, looking at the entire day, and then that may be followed up by a watch, which may be followed up by eventually a warning. There's nowcasts sort of inserted in there somewhere. So have in the CASA work that you're doing, have you attempted at all to see whether, I mean, the idea, I think in weather service, we sort of view this sort of idealized, pristine environment where our users are sort of, just entirely focused on our messages and react accordingly, etc. But we know, and your talk kind of shows this quite well, that increasingly now with this iPhone apocalypse, whatever you want, that people are kind of there's just a sea of information, and I just wonder if you've looked at, does any of this, this prepping or marination thing, does it really result in better warning response, or is people oversaturated, they don't pay any attention to all that, watch warning stuff until they actually see a funnel cloud? So that's sort of my basic question. It's kind of a long-winded one.
Well, I'd say let's see, how would I, we haven't explicitly done research on how people interpret and prepare for watches and warnings. I mean, I do think that there's the continuum, and there is, I think, other research that talks about that, and I can, find some citations and send it out to the group on that. But one interesting thing that we did in our pre-surveys of people is we asked them what was their ideal lead time, either in miles or minutes, and why did they choose that? And it came up with a median distance of about, I don't know, it was about 15 to 20 miles, and a median time of about 20 to 30 minutes. And I'd have to go back and get the exact numbers. And then people described what they wanted to do, and people had a whole variety of things that they wanted to do. Some people needed to go get family. Some people had animals that they had to take care of. Some people just thought of, well, I need to get home. But they had such a variety of things that they want to do. So I think, and the other thing, it was hard with the data that we have right now to categorize that by segment, or to say, oh, well, women wanted 30 minutes because they needed to do this, or men wanted. It was hard to use kind of traditional demographic measures to do that. And so one of my responses to that is that people are very individual in this. And so to allow them to kind of tell you what they want and when they want it is probably the best way to get their attention.
Okay, thank you. We have one question from Greg Patrick at Southern Region Headquarters, and he asks, are you in need of additional volunteers in the Dallas-Fort Worth area to use and apply the app? That is the question.
Absolutely, Greg. And if you can help with that, we'd love help with that. Yeah, because I'd love to have like 10,000 people using the app.
Okay, thanks. So another follow-up, Brenda, is from myself, is on the mobility footprints. And so, you know, it sort of follows our, I guess, mostly what we sort of perceive in terms of our traditional warnings is that, you know, people live and work in sort of urban centers, and our warnings are, you know, geolocated around those urban centers. So if a tornado or a tornadic storm is heading towards downtown Fort Worth, then, you know, we know that's going to pose a threat at certain times of the day. But the wild card is in the temporal aspect when you have the rush hour, right? So when people are mobile and are, you know, moving from one of their hotspots to another, that presents a whole different set of considerations that we've observed. The typical one for the DC area is, you know, the quarter-inch of snow at rush hour causing, you know, apocalyptic gridlock across the urban area. So that seems to be the one that's most ripe for, you know, application of these things, is when people are not in their hotspots but are moving from one to the other. Is that jive with your, you know, your research?
Yes, and I think, you know, different hazards are different. So tornado warnings, people are more likely to, you know, stay in one place and, you know, potentially be in a hotspot. For flash flood warnings or for storm warnings, you might want to look where people are mobile. And one thing I didn't discuss here is that we looked at hotspots by where people stay, but we've also looked at hotspots by places where people are rapidly moving. And if I were to show you a footprint of people's activity spaces, then their commuting routes light up, basically, and you know what those are. And so if you can anticipate what somebody's commuting route is going to be and that they're going to be impacted, and you can warn them very specifically about it in a personalized way, then that can reinforce, you know, a larger warning that's going on that says, you know, watch out on these roads. But if you get something that says your route home is going to be impacted by weather, you know, be careful.
Right.
You know, then that, a further personalization.
Right. So in the actual work in Dallas there. So when the surveys go out and people on the road, do you ask them to pull over to the side road before they answer the survey? And what do people? I mean, does your research show what people do if they they're on the road? Do they turn around and go someplace else? Do they abandon their car? I mean, do you have much data for those participants in your experiments?
Yeah, we're not doing that kind of research because we're just trying to set up the relationships right now and try to understand, what people are perceiving and doing that. In terms of the surveys, they're delivered to people and, they are, completed at a time when when they're safe. Right now, we're doing the rainfall rate surveys, so those are pretty, innocuous in terms of safety kinds of things. Where we might start a hail survey to understand hail. If we're going to ask about things like tornado warnings, we would obviously wait to deliver the survey at a time when people are safe and they're not in the middle of the event. The other thing to know is on our app, we deliver NWS warnings along with the additional information. And again, that's, something that we worked through with our human subjects board so that we're keeping people safe.
Okay, we got two questions through the chat. I'll relay them to you. Is personalization, this is from Mr. Pudai, is personalization similar to cognitive behavior of individuals? Does that make sense?
I'm not sure I understand the question, but the notion of personalization comes through the hazards literature, where they talk about how people have to receive the warning, they have to understand it, they have to personalize it, they have to, they have to figure out that action is feasible, and then they can take action. So it comes to that process that people go through when they're evaluating warnings.
Okay, and here's one from Brian Curran. He's the Science Operations Officer in Midland, Texas. It would be interesting to see the percentage of users who, when caught in a severe storm, park under overpasses. This is a huge safety issue. Have you seen that? Go ahead.
Yeah, I mean, the interesting thing about that is that, that's the kind of thing, depending on where it's located, that you could ask people, did you park under, did you go under a safety, did you go under an underpass? Would you say, well, what did you do? And you get that kind of response. We actually did a flash flood survey, and I didn't show that here. And we found that it was about 45% of people were driving on flooded roads. 55% were turn around, don't drown. The rest of the people were going through. So, so you can get that kind of information. The great thing is that it's a flexible system, so you can design surveys for people. What we still need to learn about is, how many surveys people will answer and how often you can hit them with surveys before they, before either they stop responding or they get sick of them or they delete the app and things like that.
Right. All righty, we're at the top of the hour, so we're going to have to end it now. I want to thank Dr. Phillips for a very enlightening talk. Lots of stuff to chew on here. We had a big audience, so I'm sure people got a lot to go home and think about this. And I'll remind everyone the slide set is up on the VLab Forum website, so if you want to look at that, share it with your colleagues. And in addition, within the next hour, the recording will also be up there, so you can pass that along as well. So thank you very much, Brenda, and we wish you the best. Hope to see more results of this, and I'm sure this will not be your last visit to the VLab Forum, for sure.
Okay, well, great. Thank you very much. I appreciate it.
And with that, looking for my, hang on a second. So that is the wrap up for today, and coming up in June, we have, I think we had to reschedule this one. This is Frank Alzheimer is presenting Satellite Training and Operations Resources Store, the gift that keeps on giving. And then coming up in July, we have the Extreme Precipitation Forecast Improvement Project by Diana Stovern. I think that also has some IDSS or social science aspects to it, if I recall. So we hope to see you in June and July. Lots of good stuff. Until then, everybody be productive. Signing off.